It's working. Hi, everybody. It's Isaac Raymond here in office hours again. Make sure to check out the announcements each week. I had a couple of students ask for help last week, and they didn't realize that I am posting those videos in the announcements. So let me show you where those are again. You've probably already seen this if you've been following along with me, but just to make sure everyone's in the same place. Share screen. Okay. So in our course, if you go to, actually you don't want to click home, you want to click announcements right here. But if you click home, they always pop up at the top here. So I've always got videos to help you through the content. So for this week's assignment, there's two different videos to help you through it. If you want to use Microsoft Excel and the data analysis tool pack, which makes it pretty quick, but you have to fight through getting all these things installed, you'd use that video right here. If you can't get the data analysis tool pack to work, that's perfectly fine. I've got another video for you here. And then I'm going to show you, here in in these office hours how to do the weekly assignment as well. Just like every week, we have our MyPath content. I'll post some videos in my office hours announcement that go through the questions that you'll see in MyPath. The big idea this week is we're conducting hypothesis tests. Okay, so you got two different medicines, right? Well, I mean, a big place where hypothesis testing was used in medical history was in cancer research. Okay, because early cancer researchers found out that there's certain drugs we can give to people that are overall damaging on their body, but it damages the cancer cells faster or better than it damages the healthy cells that we want to keep around. So the experiment was to figure out what type of it's hard to call it medicine, but what type of drug we give to these people that's best, and it depends on the type of cancer. You know, one type of treatment for a patient with a certain type of breast cancer doesn't work for a patient with testicular cancer or something like that because just the cells are fundamentally different, right? They're in a different part of the body. They have different things going on. So the statistics part of that is how do we know we've got 30 people that we just exposed to this terrible treatment to try to make them better? We need some sort of indication whether we should be going with this new treatment or whether we should stick with this old one that wasn't so great. And statistics can say, hey, it's likely true that this new one is having some sort of effect, some sort of better impact on the patient than the old one. Can't be sure. You can never be sure in statistics. But hypothesis testing is a way of making that decision based on the data. Okay. And it can all come down to one number, the p-value. Okay. So when you read research, if you want to know something about the results of the study, you want to look at the p-value. The p-value in a nutshell, and this is not the full scientific way, is saying the probability that the null hypothesis is true. Okay, so in last week's discussion, we talked about the null and alternative hypothesis. The null hypothesis is the boring one. The status quo means those two drugs for the cancer treatment, we're assuming that they're the same, that they actually one doesn't do better than the other one. So the null hypothesis is the boring hypothesis, means we haven't found something new with our new drug. The alternative hypothesis is the hypothesis that our new drug is doing something to help. Okay. So the p-value is the probability that that null hypothesis is true, roughly speaking. Okay. So if the p-value is low, that means there's a low chance that these two drugs are roughly equivalent. That means we found something here. So a low p-value is actually what we're looking for because we want a low probability that there's nothing going on here. We want a probability, we want to know that for sure our new treatment's working. It's an interesting history. It's a sad one, obviously, because we had to experiment with people going through some terrible, terrible treatments. They discovered mustard gas at one point. I think that it was used either World War One or World War Two. I mean, I know mustard gas is used in World War One, but I think something happened in World War Two where mustard gas blew up on a ship, and they discovered something about cancer somehow that way. But they actually started using mustard gas as a chemotherapeutic in some form, and it was actually working. It was like it was reducing the cancer cells faster than reducing the healthy cells. I don't know where it stands today, if there's some sort of like offshoot of that mustard gas stuff, but that's the terrible mathematical history of trying to help people with cancer. Dana-Farber, sorry, this is a little off topic, but if you know anything about cancer, you probably know something about Dana-Farber and the Dana-Farber Institute. Dana-Farber was just doing guesswork, trying to figure out how to help people. So there was, what was it? Oh, it was children's leukemia, some form of children's leukemia. Dana-Farber said, okay, I guess these are white blood cells. We don't really have a lot of scientific technology to distinguish a lot of the white blood cells like we do today. Dana-Farber was like, okay, so let's try to give him this vitamin B because I know white blood cells like vitamin B, and that accelerated the cancer. He accidentally pushed these children's cancer further into the like it proliferated because he was giving the cancer cells exactly what they wanted. So he stopped the treatment immediately, and then he did the opposite. And he said, "Okay, let's take away what white blood cells crave." And I think it was vitamin B. And they did some sort of treatment that was reducing the vitamin B, which hurt the children because we need vitamin B, but it hurt those cancer cells faster than it hurt the healthy cells because that's what the cancer cells desperately needed, and he was able to extend their lives by a couple of years, and that's one of the first big steps into chemotherapy. Okay, so a little bit of every teacher does that, right? They have like but they find it really exciting to share with you about a particular topic, and it depends on what your area of interest is. Um, so, all right, that's why. That's why we do it, because we need to know whether this new drug is better. We can't be sure. Is the difference big enough between these two? That's what you're going to be doing this discussion board. As of this writing, the discussion board is not working as anticipated because there's a federal government shutdown. So if that's the case, when you're taking this course, you'll see I've posted extra instructions down here in case that website's not working. Where is it? Right here. The website's still down. You can just go to this website. All we really need is numbers from 2 different years. So we need like the average grade level, uh, the average highest grade level of a household. Um, no, maybe that one won't work. So, oh, how about this? The percent of households that have a bachelor's, at least one bachelor's degree. That might be a number you look up. Okay. You find it out for 2000, then find it out for 2020. That's it. Those are the two numbers you need. The percentage of people with a bachelor's degree in 2000, percentage of people with a bachelor's degree in 2020. That's enough for what we want to do because that lets you set up your null and alternative hypothesis. And that's what this discussion board is about. Okay. So for this discussion, that's the goal. Set those two things up. If I find those two numbers, give us a little bit of background, and then address these points. Okay. And so when you say your null hypothesis, remember what I said at the beginning, the null hypothesis is the boring hypothesis. So for my example, the null hypothesis would be that there's no difference between 2000 and 2020 in percentage of households that have a bachelor's degree. The alternative hypothesis is that there is a difference. Okay. Remember, because the null hypothesis means there's no effect. What you're going to find is there's always a difference, at least in the numbers you've got, but that could be just due to random chance. Maybe in 2020, there just happened to be a bunch of people that moved into this county where you get your data that have a bachelor's degree and boosted the numbers. There's always some random chance happening there. Is the difference big enough for us to say something happened between 2000 and 2020 that made the bachelor's degree increase enough? And when we actually conduct a hypothesis test, which you don't have to do in this discussion, calculate that p-value, that that tells us whether the difference is big enough to claim that there's a statistically significant difference. Okay, so that's the goal of the discussion board. Find a number that happens in like in one particular year, find a number that happens in another particular year, then post those numbers. Okay, so that's the discussion. We said my path. Basically, we're talking about the p-value. I've given you some instruction there. But check out the office hours announcement that I'm going to be posting soon. Okay, then this week's assignment. Let's go to Unit 6. So this week's assignment. I showed you where those videos are, but I'm going to go over one of those. I'll go over both those processes that you can take. Oops. Okay, so for this week's assignment, um, you are writing the null hypothesis, which should be the hypothesis that there's no difference in the two groups. You can just state it in words, like I've been saying in words here. Run the analysis either using the data analysis tool pack, which I show in a video, or the two sample test by comparing two confidence intervals. I'll do both of those for you, okay? The first one, which automatically gets done in the data analysis tool pack, is to conduct a hypothesis test and hopefully eventually get that p-value that we talked about. So when you're comparing two groups, you're calculating a test statistic, which it's a t-value almost all the time when you're talking about means in practice. Z is rarely used because you have to know the population standard deviation. The difference between the two is subtle, and it really matters a lot less as the sample size gets bigger. But technically, we're supposed to be calculating a t-value. What you do is you subtract the two means, and then divide it by the square root of the standard deviation. Sorry, the variance, I should say. So the standard deviation squared of the first mean, divided by the sample size of the first mean. These are just numbers that we'll get. And then add it. So we're pooling those two standard deviations. Well, no, I shouldn't say that. We're pooling those two standard errors. This is a more correct way of saying that. That's the formula. These are means. These are standard deviations. This is the sample size. And let's see, what do they want us to do? They want us resting heart rate. They want us to compare resting heart rates. So I'm not going to do that because I don't want to give away the answers. I'm going to do it for after exercise. What I want is the mean for males and the mean for females. This is for after exercise. Just emphasizing that because you're doing resting heart rate according to the instructions. So the means are these numbers up here. I'll make this one the males and this one the females. And we saw how to do that in a previous video. Type equals average, open parentheses, and then you click and drag for all the males, all the zeros. Then close the parentheses. I've got my mean for the males. And the mean for the females equals average, open parentheses. You want to click and drag all the females. I'm doing the after exercise, but you're supposed to be doing the resting heart rate. There they are. They're pretty close. Females is a little higher. They could be just higher just because of random chance. Okay. So next we need to calculate the standard deviations according to that formula. Oops. Standard deviations. Well, let's do variance because this is the sigma is standard deviation. If you square it, it's the variance. So let's just get the variance equals var dot s, just like we did before. Open parentheses, then click and drag for the males. Then close that parentheses. And then we want to do the same thing for the females. Look, I'm just going to copy these. These are saying the cells we want to use. So type equals var.s, open parentheses, and I'm going to paste. It's the same thing as clicking and dragging though, okay? Okay, pretty big difference in the variance. And the last thing we need is a sample size. So this starts on 5. It ends on 112. So 112 minus 5, then we got to add 1 because of inclusion. So it's 108 males. And you can do the same for females. Starts on 113, ends on 204. So 204 minus 113 plus 1, that's 92 females. That's that sample size, the bottom part of the formula. Now we can plug those numbers in. I said males is going to be sub 1, so that's males, it goes there, subtracted by 91.2 for females, divide by the variance for males was 61.2 when I round, and 108 for the sample size. So I just plugged in numbers in here that I got. And then for females, the variance was 30, well, that rounds up, 35. Sample size was 92. Okay, and then the rest of this is stuff we did in our previous math courses. You want to simplify using the order of operations. Nice and slow. So we'll subtract the top. That's negative 0.9 for the top. And in the bottom, I'm going to do the fractions first. 61.2 divided by 108, 0.56 repeating, 0.567, and then we've got 35 divided by 92, that's 0.38. And then the bottom, 0.567 plus 0.38. That's the square root of 0.947. Almost there. Now we need to take the square root of the bottom. And I'm going to copy this to my clipboard. So it's negative 0.9 divided by that number. So drop the negatives, negative 0.92. That's our t value because we said t equals all this stuff. Okay, and then what you can do is you can Google search t value to percentile. It's going to ask for degrees of freedom here. We'll use a rough estimate. So that's negative 0.92 for our t-score. You can use any of the calculators on this list. And then the degrees of freedom, when there's two samples, there's a more complicated formula, but we'll use an approximation. Add the two sample sizes. We had 108 for the males, 92 for the females. That's 200. And then subtract it by 2 because there was two parameters that we used. And then if you hit calculate, it should give you a p-value. There it is, 0.179. So that's the big thing that we talked about before. That's the thing we want. The p-value is 0.179. So what you would say is that the p-value is not that small. That means the probability that the null hypothesis is true, given our data, is roughly 0.179. That's not exactly the p-value. If you want the full definition, the p-value is telling you the probability that you got that test statistic of negative 0.92, assuming that the null hypothesis is true. So it's an 18% chance. So that's a relatively still big chance that the two are actually still equal to each other. So we're not going to say that there's a difference, right? Those sample means aren't that far apart, so that makes sense. We're not going to claim there's a difference between the two groups. If the p-value you get for your numbers is like 0.04, that's below the typical cutoff of 0.05. So if you're wondering where we count with 0.05, it's just a number we've all agreed on, and that changes based on the circumstances. Like if you want to be really sure before changing your chemotherapy treatments that the new treatment is good, then you drop your alpha, that 0.05. You'd say, I'm not going to use 0.05, I'm going to use 0.01. My criteria is stricter. I want to really make sure my new treatment's working. And if it's not as dire, then you can use 0.05. But those are just arbitrary cutoffs. So the p-value is not low. So that means we fail to reject the null hypothesis. So you can do the same type of thing, get the same results using the confidence interval, like you'll see in the video I posted. That's exactly like what we did last week. You make a confidence interval for both of these. Okay, so the formula for the confidence interval is take your mean plus or minus the margin of error. So this is usually a t-value times the sample standard deviation over the square root of n. Okay. But you could also use the calculator-based approach, just like you did in your assignment last week. So let's say you got a confidence interval for this first one, and it was 88 for the lower bound and 92 for the upper bound. Just made up some numbers. That's not quite it because the mean's supposed to be in the center. And if this one was 90 for the lower bound and 94 for the upper bound, so this means that if we was a 95% confident interval, we're 95% sure, 95% confident that the true population mean for males is between 88 and 92. And likewise, 95% confident that the true mean is between 90 and 94 for females. So what you want to do if you're using the confidence interval approach is find out if these two intervals overlap. So if I was to graph these on a number line, here's number 88, here's number 92. I'll put this in blue. That's our males. And then females was 90 to 94. Put that above in red. They overlap, they cross right here, right? So if there's an overlap, that means you can't say that they're different from one another, right? Because there's a possibility, since the true mean for males could be here, the true mean for females could also be here. There's a possibility that they're still equal. Um, so with the confidence interval approach, make your confidence interval for both groups, and if they cross, that means you fail to reject the null hypothesis. Can't say that they're different. If they don't cross, if the second graph looked like this, there's no overlap, right? So those are the two approaches. You got those two videos I made for you too. Either one works. I think that covers basically everything. I'll put those My Path videos up on the announcements too. If you still have questions over this, because I know I've gone over a lot of material that's new, let me know. The p-value thing is weird, so if you still feel weird about it, that's okay. Just remember, the p-value, roughly speaking, is the probability that nothing is going on here, that there's nothing significant, nothing important. If that p-value is low, that means it's kind of like a double negative. There's a low chance that nothing is going on. Okay, if you have a low p-value, that means something statistically significant happening here. Okay, so you got my email, iraymond@herzing.edu. Please let me know if you need anything. Keep reaching out to me if you have been before. I've been talking back and forth with some of you, and I'm happy to keep doing that. Just let me know whenever I can help you, okay?